present. All right, everyone. Welcome to our fourth lecture on Battlecode. Today, we are going to be going over intro to communication. But before we do that, here are some of the latest balance changes and bug fixes that we've had. You can read over them if you're already live. For the first bit, so the main thing that you'll be using to communicate is a global shared array. Each team has one. There's 64 slots on it, and each slot is 10 bits. They can store integers from between 0 and 1023. So this is going to be your main method of communicating between your team. The most important thing you want to note here is that only the rat king can write to this global array, and all of the baby rats can only read from it. Of course, reading and writing is going to cost you bytecode, and writing is more expensive than reading. Specifically, it's 50 versus 10. So how will the rat communicate to the rat king on what to write? What they can do is they can squeak. Squeaking costs bytecode. It will basically send out a signal, and you can attach a message to your squeak. It will have a distance of square root of 16, which is 4, radius of 4. All entities on the board will hear your squeak, both your allied rats, enemy rats, and the cats. So this is a dangerous move, but necessary to communicate. If you can use squeaking to your advantage in more than just like communication. You can use it to get the enemy rat's attention, or you can get the cat's attention. You can lure it somewhere, you can lure it away. But the main method is, of course, to communicate messages to your allied rats in order to get them to the rat king. And of course, it costs like to squeak out loud, like to the other players, the other rats, and also to read the squeaks. And squeak will remain available for the previous 5 rounds. So you can either decide to read like the current round's squeak, or you can decide to read the previous round's squeak as well. And so you could use that to your advantage. So how do you store a location? So one thing that we want to talk about today is storing a specific location in this global shared array. Location obviously has an X and a Y, and we'll see the most optimal way of storing this. So what we can do is we can compress both an X and a Y into a single integer and store it inside our global array. So what we can do is, if you look at the 3 pictures on the right side, this is a basic solution, but it's a very basic example. But we have a 3x3 square labeled from 0, 1, 2 and 0, 1, 2 both on the X and the Y axis. If you just store the X and the Y separately, you would have to use 2 slots just to store one single position. But if you assign each slot a unique number, for example, on the second image, you assign the bottom left one to integer 0, and then you keep going up to the integer 8. That way, you can just use 3 integers to store 3 locations. However, this is a really good solution, and this is what you want to be using. But there is a little bit. There's one thing better that you can do, which is reserve the 0 slot. It is used to represent unused array index. And what's that used for?
But yeah, basically, like if you're communicating with, like, let's say you're racking and communicating with all the rats on the team, you can use this extra 0 value. But like, oh, we haven't figured this out yet. Like if you're keeping a slot open for like the location of enemy racking, you can basically just set it to 0 until you find it, and all the rats know you haven't found that enemy racking yet.
Okay, cool, thank you. So one very important thing is that because you're limited to only 10 bits, which is numbers up to 1023, and because we have maps that are pretty large, you aren't able to exactly store all of your X and Y's, like your coordinate systems, inside one number, because it will be larger than 1023, obviously. So you're going to need multiple indices for each location. And so we have a pretty good way for storing, pretty optimized way that we'll show you later. So what do you want to store? Like, what are good things to store inside your global room? Well, it's up to you. You can store whatever you want. You can do like cheese mine locate. For today, we're going to focus on showing you how to store cheese mine locations, where the enemies are, enemy rats, and also cats. But obviously, you can apply our principles that we show you today to whatever you want. It's up to you. For example, you could do the rat king locations. For example, you could not only do enemy rat king locations, you could also do where your other rat king locations are. You could do all the trap locations. Um, for example, you could figure out maybe where there is an enemy rat trap. Maybe you could correlate that to there are going to be other rat traps in that area. You can also check number of enemies, how much cheese you think the other team has collected, how much damage you think the other team has done. So you can try to see if you want to backstab. It's all up to you.
Cool. So now that we've gone over the slides, I'm going to do some live coding again. I'm going to show you how to implement the stuff in Lecture Player, and then after the lecture, I'll release it all. So you can GitHub repo the Lecture Player's on right now. So let's get started with that. Cool. Looks good. Here's Lecture Player. And the first thing we're going to do, just close this, is we're going to make the rats tell the rat king where the cheese mines are. And then the rat king's going to tell all the other rats where the cheese mines are. So that way, like, finding cheese is a lot more efficient. So I guess I'll put that one.
All right, so here we're just basically we're getting all the nearby information, the map information on a rat, and then we're going to originally we checked to see if there was cheese there, and we have logic for doing the cheese, but now we are going to check to see if it's a cheese mine.
Cool. And now that we have that, the rat should be able to recognize where the mines are. This is for, remember from last lecture, we have a state machine. Let's say this is in its fine cheese. So if the rat's in the fine cheese state and sees a cheese mine near it, then it's going to store this in the mine location static variable. And since the static variables are not actually shared between robots, each robot has to be one. And then when it gets near the rat king, we want to squeeze this information to the rat king, and then the rat king can broadcast it to all the rats. So the radius square right now we're checking here is 8 because that's the approximately the transfer radius, I think. But we actually are going to check for 16 when you're trying to just squeak. So instead of putting it in this block where we actually know what the king is, we're just going to compare against the king location variable right over here.
Yeah, because our squeak can only contain integers, so we can't squeak the map location. And so now we're converting the map location into an integer, as we talked about earlier, trying to convert a coordinate into an integer that you can share. And so, as I talked about earlier in the slides, if your map is too large, you can't store it in one integer, and you have to convert it into, you have to split it into two different integers. And so, checking that logic here.
It looks like the AI is not coding what I want, so I'm just going to write it manually. We basically want to extract the 10 smallest place value bits from this integer, so we're going to do 2 integer location, and then we just have to take it mod whatever 2 to the 10th is. And the reason we're using 10 here is because 1023 is the highest number that can be stored in so when we're racking process is so we're just going to say 4 for this. And then for larger place values, we can just use this operator here, which is the redshift operator to get rid of the smaller operators. And I think we're good now. We can just squeeze the integer, and then actually this is interesting because we kind of want this parameter to be an integer because like the racking is going to have an integer value for the squeak. So instead of that, we're just going to do this. So now we basically have these functions, which will be pretty useful, and we're going to use them. So let's find return to king. Let's go to, here we go, squeak to ensure my location. And then when the king receives this, then we need to broadcast to everyone. So let's do that.
And this just being the sweeps for the current round, you can get the sweeps for the previous 5 rounds as mentioned before.
So here, locations 2 and 3 represent the first and last integers of a mine location. But the thing is, we want this to be able to handle multiple mines. So we're going to have to change this a bit. So let's make a variable globally for the racking. It's going to be called, let's see, I guess number of mines. 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 And what we're going to do with this variable is track like the total number of mines, and this is useful because then we can know exactly which indices of the shared array are taking mines. So instead of 2 and 3 here, since this is a new mine that we found, actually we need to compare it against the old mines. So let's do that. Let's just keep an array of all the old ones. Also, so public static int array mine. Actually, yeah, mine locations. Actually, since we're going to be making this larger, we want array list of integer, and we're good. So, yep. Question.
I have a question. Given that there probably won't be that many lines, would it be a good idea to just make an array that's has a little bit of extra space and then just find more?
So in terms of bytecode, I'm pretty sure that would be better. I'm not 100% sure because I haven't tried out array list of bytecode and like looked into the details, but I'm pretty sure that that's a good idea. I don't remember if there's an exact like, cap on the number of mines in this spec, because for large maps you could have a huge number of mines, but like as long as you make sure. But yeah, just for this basic example, we'll just be seeing this. Now, the last thing we need to do is make the route actually care about the broadcasted mine locations. So now we're going to go to run find sheets, and we'll basically say to like go towards the mines. I think we do want exploration as well, so we're going to have this be probabilistic. We're going to say like half of the routes that lead to go find sheets are going to be the existing mines, and half are going to try to explore. And then if you want to modify this, you can say once you reach a certain number of mines you know about, you can kind of like stop exploring at all and just go to the mines you know about. But like for this, we're just going to do the basic always explore 50% probability.
And that's just the random logic for determining 50-50 whether you're going to explore or put the cheese mines. I believe we're going to get a random cheese mine. If we are going to go look for a cheese mine, we're going to get one from the array that the cheese mine list that we have, and then go to it. And that was just getting the application from the two integers. And that's just very basic pathfinding logic, going straight to the cheese mine and removing all dirt that's in the way. And of course, getting the cheese.
Then once the rat has reached the mine location, we want to, well, we can basically just do nothing else because there's already logic at the top of the function for looking for nearby cheese. And then once it finds the nearby cheese, it's just going to go towards the cheese. We do want to make sure that this thing right here doesn't run when it is going towards the cheese, because that'd be bad. So we're just going to set target to off. Cool, so now we basically implemented the whole thing. Let's go back to everything we have. So we've converted the location to an integer. And then we've got the first integer here, last integer here. There's one last thing to do, which is like we have to decode this integer to integer because we're basically storing the target cheese map location is an application. So we're trying to be really careful about how we define this application. Final references here. Since there's no references, I think yes, it's extremely weird. We just do a normal search, and we set it right here. So this just takes the two array things and puts them together, which is like wrong. So for that, we're going to say int encoded location, and then we just put them together. Yeah, so we're going to take the larger bits, which I believe is y. Yep, get last bit. Take the larger bits and multiply them by 2 to the 10, which is 10 times 4 times x. Now we have our code location. And set of x and y here, we're going to do get x code location, get y code location to find these functions too. There's a lot of steps when you're using shared array. And there are definitely more efficient coding methods, which I'm going to talk about in a minute. But this is just like a way that works. So check if this is correct. Mod 24. No, this is not correct. The AI. So instead of that, we're going to go back to this. And remember, basically, there are 6 bits for each of the x and y. And what that means is, well, basically look at this and see that like x is the larger bits and y is the smaller bits. So to get x, we're just going to do like shift, coded location, shift right by 6 bits. And to get y, we're going to do coded location mod 64. And that should be correct. Yeah. So now I guess it's time to test. So let's actually make this easier. Let's go to run find cheese and output an indicated string, depending on whether it's exploring or not. And now we can test. Let's do this. So we have a lot of errors, and this is not actually an engine error this time, I think. This is just an error in my code. Let's briefly look where it is. Use code, that's not correct. Run find cheese. Number of lines must be positive. So I think this is happening because we're choosing a random number from 0. So we want to say, like, you can't be in the targeting mind state before. So where's that state? Run find cheese right here. We're just going to say run find cheese. If not this, not explore and find cheese, but there are also no cheese lines, then explore. And this should be good. So let's try running it again. But there we go. Cool, no errors. So let's look at what it looks like in the client. This was default medium, I believe. Lecture player versus lecture player on default medium.
Just do date modify the latest one.
Oh, true. That's a good idea. Yep, there we go. So let's look at this a little more carefully. Look at those indicator strings. Go really slow. Starting right here. This rat is exploring, which is good. This one's also exploring. That's not collecting cheese. This is also exploring. So it looks good so far because I don't think they know where any mines are yet. So this one probably saw a mine. So let's see what's well, that's there. So this one right here is also exploring, but we see it not more rats. At some point, we should see a rat that's targeting a mine. There we go. Is this one? Oh, it's not find cheese. It's that one. No. Here we go. Another new rat. It's not. I think we might have just gotten unlucky with our random number generator at this point. This is this one. Yeah, none of these are actually targeting, so let's change it up so we can actually see one. But if this doesn't work, I'll just move on to the next communication strategy, and I'll publish everything to on GitHub.
Should we also make the probability of
Yeah, that's a good idea. What's it called? Next Boolean.
true?
Yeah. This is really bad, but I'm just going to do something extremely simple. Next Boolean, and we're going to take the and with the next Boolean. You should use integers instead, but this is fine. So let's run it, see what happens. Well, it looks like the robots didn't actually find any cheese mines, which is very interesting. Or they didn't get back to the Rat King safely. So let's just set another print statement. This will be the last one I do. This is going to be in run find cheese. I'm just going to say when we get to mine, then where's that? Yep, if it has that, then print. This is the kind of debugging you usually do if something's not working correctly. Found cheese mine at this location. Let's check. And there we go. They found some cheese mines. It looks like the cat's probably destroying all the rats before they can get back safely, so they never report to the king, but they at least found them, which is the first step. Hopefully with better strategies, like maybe the ones I'll put later, or the ones that pathfinding strategies that people will put in the later lectures, they'll be able to actually contact the king. So now let's move on to some other communication strategies. Cool. So I just want to briefly talk about one thing to do to make this packing of integers in your array more efficient. Basically, you can kind of compress them. So like each map location can be stored in 12 bits, no matter how big the map is, because the map is like capped at 60 by 60, right? So 3600 is less than 212, which means it takes 12 bits to store this map location. But it only has 10 bits of space in a shared array for each integer, and there's 64 bits. So what's like the best you can get? Use a whole shared array for map. Let's do this map right here. So you're going to have 10 times 64 total bits in your array, and then you divide by 12. So you can theoretically pack 53 map locations into this array, which is pretty good. And the way you do this is just a bit arithmetic like this. So you're going to say like, let's see, like back here. see the blackboard. Well, that's too bad. But yeah, you basically just take the bits from each of your applications, concatenate them all, and then split them at each like 10, which is a pretty simple thing to do. You can get AI to do it if you're not familiar with like binary arithmetic, but yeah, it's a good idea. But now that we've done that, we're going to implement some enemy rat spotter messaging. If you see an enemy rat, what you want to do? One good strategy is just like broadcast to nearby allied rats that you saw it, so that they can like stay away. Or especially if there's a lot of them near enemy rats nearby, this is great. So we need to want that. And also, if you see an enemy rat game, then you probably want to tell your own rat game so this can be broadcast locally. Even though the location can change, it's pretty slow. So if we get back to your game time, then it's only going to be those few squares off. And then you can kind of target it by setting your rats that way. Another thing is capitalizations, but like for those, since they move pretty quickly, it's usually not going to run back to your racking and say where it is unless you're just using a general location on the map, like a more coarse grained thing. So you can just message some nearby rats and run away. So let me just implement a few things right now.
And besides just running away, you can obviously look to the pattern by the
And now that we have multiple squeaking methods, we need to come up with a way to like figure out what kind of squeak this is. If this is like, oh, here's where a cheese mine is, or if this is like, there are this many enemies nearby. So let's add like an extra few bits to our squeak to just indicate this.
Here we're just converting the num to an integer so that we can squeak the correct integer and then determine will convert back to the type.
So now to do this, we need to figure out how many bits are in our squeak. To put this number back here in front of it. So let's just calculate that. For applications, our squeak is just this 2 integer, and this is 12 bits. And then for the other one, which is like the number of enemies, that's going to be really small, much smaller than 12 bits. I'm going to to this location. So we're just going to modify it to the left. The operations are suitable for communication. So now we have this, and we don't have but just yes, so we just say 1 if it's enemy racking, 2 if it's enemy count, and 3 if it's enemy cheese mine, or 3 if it's cheese mine. There's a better way to write this, but it's good enough. So then we can go back to our squeak methods and use the encoded value, get squeak of cheese mine and other.
After reading the sweep, you can figure out like how many, you can maybe determine a way to figure out how many, like, what you should do depending on the number of enemies there are. Maybe go trap them, or go attack, or run away. There's too many.
Yep, and another important thing here is whenever you encode your squeaks, you also have to decode them whenever you do get squeaks or what's called read squeaks. So be sure to do that. Let's do just set like a get squeak. Looking small again. Save this here and also get squeak value. So let's define an integer squeak equals this, and then get a squeak type of squeak, and this is actually an array, so we're going to do that squeak, and then squeak values and squeak types. So this is message. Oh yeah, sorry, we should actually do this here. For each message, we have a code rotation. This is no longer that. This is going to be and squeak equals, which method do we actually want to use here? Yeah, it is good. Here we go. Encode location is just going to be the squeak value of raw squeak. And then we want to say if get squeak type of raw squeak is not cheese mine, then we don't care. That will change later. We have rack kings that we're finding. I'm actually not going to implement that right now because it's so similar. You basically just do this exact thing and just have an extra bit for whether it's a rack king or a cheese mine shared array. So you can do that, and I'll put that in my play too. But the important part right now is these get squeak value methods. So I'll just implement them in case you're not familiar with these binary operations. Squeak type, get squeak type. And recall that this is just the number here, which is shifting as well. So let's do that. Return raw squeak shift to 12, and then we need to convert this to the actual value. So we're going to just do a nice thing up here to save bytecode. We're going to say public static squeak type. Squeak types is squeak type of values, and just computes it once. So we can go down here and then do squeak types of that. And then we can do get squeak value, and I think this might be correct, but let's just write it in a more normal way. We can do mod, and it's going to be 4096 because it's 2 to the 12. And then we're good. You might want to include some checks here that your value is actually below the 4096 number, but like this is never going to go in our example. This does not exist. Everything else is good. So let's work on the return to the racking and explore. This isn't really communication, so I'll just breeze through it. Let's do return to racking and explore here. Case. And actually, this will be the same as return to king, except you just don't transfer your keys. So we can actually do a cheat here, which is if, I don't know why it's not autocompleting this, but current state is state find cheese. If we switch to that state afterwards, then go back to explore and attack. And then we do want to modify the return to king method so that we can communicate to the rat king exactly what's going on. But that's something that I'll do later because it's exactly the same. It's just squeaking to the application. Yeah, so that's pretty much everything for tweaking the enemy rat number or king. We need to somehow use the information now. So we're going to say if you're exploring and attacking and you see a large number of rats in your squeak message, then maybe you should like run away. But the problem is we don't actually state the direction the rats are in, so we can't do that right now, which is what I'm going to do. But they included in the microphone. The way to do that. So now I'll just go through the last stuff. Important ones like if you see the cat spotted, then just run away and squeak to like all the neighboring rats so that they don't get caught. So to do that, in the explore and attack phase, you can also add this but we basically want to explore location and the direction or so you want to check if there's a cat nearby. So nearby enemies. This actually does not include the cat because it's using that opponent team. So another call nearby cats. And this is going to be, also this is very bytecode. So by the way, you might want to optimize this by like storing the application between rounds. So also broadcasting them, the general locations is also a good idea. But for now, we're just going to do this. Since nearby robot, we want team dot neutral for the cat. And then for each there's at least one cat. We do not need to be 0 enemies, so I'm going to get for enemies create 0. So we're good there. And if there's at least one cat nearby, then you're going to make a new squeak cat found. And of course, remember to do this. Here's a way around this method so that you don't have to update each time. You should probably do that. You basically just get this number from the thing itself by calling like dot ordinal, I believe. You see type dot, yep, type dot ordinal. But just do that. So squeak type dot cat found. And then instead of the location, you're doing the direction because all the squeaks nearby, if you draw it out, which I'm not going to do, so people can see it on the blackboard, but you can imagine like you have your cat somewhere, and then you have like your rat, let's say 4 squares to the right. If you squeak around there, then all the robots near you are going to receive the squeak, and all the ones on the other side will not. So it's fine to say direction in this case, but you have to make sure you're far enough away from the cat So for this case, we're just going to sweep the direction. So let's say direction. We can actually sweep it as ordinal here. So get direction here, direction. And we're just using 0 because like chances there be multiple cats is pretty low for the default maps we're providing. So direction to the cat. Just check if the distance is large enough. If the distance is not, then move away from the cat. So if, let me go here actually, if this that, so it's 3, this is squared, so at least 9. Distance squared to the cat is at least 9, then we can do found a cat indicator string, and we can also do all of this stuff. Yeah, so the squeak radius is like 16, so you don't actually want to alert the cat that you're there. So instead of 9, let's do 17 for this. If you're outside the squeak radius of the cat, then you want to do it, but also what's the vision radius again? You need to check that. So let's just go. Be right here. Very good to reference this back. Rewriting strategy. Vision radius. Let's go. Or actually the RAS units. It's the cone thing. Where's right here. You can sense stuff in other robots up to square root of 20 meters away. So this does work. If it's between 17 and 20, then we do sense it, and this is good. So direction to cat, and then we just want to cat dot ordinal. And I think this is it for the squeak. And then we need to retrieve the squeak. When you're in explore attack, you should read all the squeaks. So let's do that. Or it moves. Say, do the same squeaking thing. Get squeaks at the current round number. You should probably make this be all the round numbers recently in case robots go in different orders, but let's keep it as this. So then for squeak and squeaks, it generates a huge amount of code. We don't want that. We want to get the value raw squeak. And then we're going to say like if the type is not the cat found, then continue. But if it is cat found, then direction we can compute, and then we can move the opposite direction. If RC can turn of way. You should of course modify this so that it tries all the directions close to away in case it can't get away. But extra stuff. There's so many like small things you can add to strategies which might be useful. But yeah, I'm gonna wrap this up in a minute so we can have time for office hours. But let's just finish this part. So if you can turn away, then turn away. If you move away, then move away. And if there's dirt blocking your way, of course you want to take dirt. So I think this is pretty good. So now everything will run away. We do want one more thing, which is like, if you go to squeaking here, if you find a cat, you should also run away from it if you're closer than 17. So we do that, and we do that. It's the same thing. You should abstract all this. Remove dirt. If you can do it. And that's it. So let's just test this. I don't actually because there's electric player. But Just check. Looks like there's an error. Let's see, this is the explored attack. Directions of direction ordinal. Huh? Direction ordinal is huge. The squeak type is not cat found, then continue. 4. So let's, when we squeak cat found to cat.ordinal, then we are just print out the print line of the direction of squeak. So, to cat, and let's just do ordinal. And let's just make sure the squeak is received correctly. So if we go to, it's going to be if get squeak type is not cat found, then continue, and then get squeak value is this system the line of direction ordinal. So it is 1434. Transfer. It looks like a map location actually. So I'm pretty sure what it's doing is it's not receiving its squeak types correctly. Oh, I think that's because this is not supposed to be 1 indexed. So what we have to do is we make a new squeak type called invalid. All the indexing is set correct. Because the arrays are 0 indexed, but everything down here is 1 indexed. Now, okay, looks correct. That's one of the directions. And then, do we ever receive cat? Looks like we don't. Okay, that's kind of to be expected because there aren't that many rats. I think this is correct. So I'm going to push this changes to GitHub, and if there's anything else I should talk about before we end. Wrecking, stats, cheese, packing this. Yeah. Also, empty spots on the map. It could be useful to capture. If you see like there's nothing there, just report back that there's nothing there. So people don't waste time exploring, especially in the initial phases. There's many other things you can do with communication. The main issue is just like getting all this information back to the wrecking and incorporating it all into one shared array. So it can be going to communication sometimes, but once you get it, it'll be really useful. Anything else you want to say?
I don't think so.
Cool. So yeah, we'll stick around for rock stars. There might be if you want to take some extra and ask us if you have any questions. Good luck. Thank you.
Thank you.
What's the limit for how long it's can be?
Oh yeah, I think it's just a measure. So it can be 30 minutes. So it's really powerful compared to the sugar array, which is 10 minutes. Because I don't think we have a constraint on that.
I think if there's like some way like it's a path to the line, it's weird and you can't just go.
That'd be really cool. We could like save a lot of bytecode that way. I'd be real interested in seeing some strategies like that.